everybody. In this section, we will study about force acting on two parallel infinite straight current carrying conductor. We will use this knowledge to define SI unit of current. This is followed by the torque acting on a current loop placed in a uniform magnetic field. We will also define magnetic dipole moment, and we will also derive the expression for magnetic dipole moment of a revolving electron. Thereafter, we will discuss about moving coil galvanometer. We will use the concept of moving coil galvanometer and to convert a galvanometer to ammeter and voltmeter. First, let us discuss about force between two parallel infinitely long current carrying conductors. Here we have two conductors PQ and SR, both carrying current I1 and I2 in the same direction. Since we know that a current carrying conductor produces a magnetic field, the current I1 produces a magnetic field at Rs, which is given by B1. B1 is the magnetic field produced by current I1. By right hand thumb rule, the direction of B1 will be perpendicular to this page and inwards. Now, the expression for B1 is given by mu0 I1 by 2 pi r. B1 is perpendicular to Rs and inwards. Since Rs carries a current I2 and it is placed in a magnetic field B1, it experiences a force, and the force acting on Rs is given by F21 equal to B1 I2 L sin 90. Here the angle becomes 90 because the magnetic field and the direction of current are perpendicular to each other. Therefore, F21 is equal to B1 I2 L. The direction of F21 is given by Fleming's left-hand rule, and it is found to be horizontally towards left as shown in this figure. Substituting for B1, we will get F21 equal to mu0 I1 I2 L by 2 pi r. Similarly, the conductor Rs carries a current I2. This will produce a magnetic field around it. Hence, the conductor PQ is inside the magnetic field produced by the current I2. The magnetic field produced by current I2 is given by B2, and it is given by the equation B2 equal to mu0 I2 by 2 pi r. The direction of B2 is given by right hand thumb rule, and it is perpendicular to the page and outwards. Now, the conductor PQ carrying current I1 is placed in a magnetic field B2. Hence, it will experience a force. The force acting on length L of conductor PQ is given by F12 equal to B2 I1 L. Substituting for B2, we get F12 equal to mu 0 I1 I2 L by 2 pi r. The direction of F12 is given by Fleming's left-hand rule and it is horizontally towards the right, as shown in this figure. If you look at the equations F21 and F12, they are equal in magnitude but they are opposite in direction. So the net force acting on the length L of any conductor is given by F equal to mu 0 I1 I2 L by 2 pi r. The force acting per unit length of these conductors is given by F by L, that is equal to mu 0 I1 I2 by 2 pi r, the unit Newton per meter. So the force acting per unit length of the conductors PQ or RS is given by the expression mu 0 I1 I2 by 2 pi r, where r is the distance between the two conductors. We can use this equation for defining a SI unit of current. The unit of current is ampere. Now we can define 1 ampere using the above equation. Let us assume that when I2 equal to 1 and R equal to 1, then F is equal to mu 0 by 2 pi. Mu 0 having the value 4 pi into 10 raised to minus 7. This equation simplifies to 2 into 10 raised to minus 7 Newton meter raised to minus 1. Hence, we can define 1 ampere as follows. 1 ampere is that current which, when passing through two parallel conductors of infinite length and placed 1 meter apart in vacuum, exerts a force of 2 into 10 raised to minus 7 Newton per meter on each other. Torque acting on a rectangular current loop in uniform magnetic field. Here we have a rectangular loop PQRS placed in a uniform magnetic field of strength B. The loop carries a current I. The breadth is B and length L. We know a current carrying conductor placed in a magnetic field experiences a force. The force on PQ is given by F equal to BIL sin theta. Here, theta is the angle between magnetic field and the direction of current. That is 90 degree, and hence the force is BIL. The direction of force is given by Fleming's left-hand rule and it is perpendicular to PQ and outwards. Similarly, the force on conductor RS is given by F equal to BIL. The direction of this force is perpendicular to RS and inwards, as shown in this figure. These forces are equal in magnitude but opposite in direction and separated by a perpendicular distance. Hence, they constitute a torque. Torque τ is given by force into perpendicular distance. To calculate torque, we draw another diagram where we look at this rectangular loop from above. That is, we are seeing PS as shown here from above. Then we see that these two forces will be acting opposite to each other and they are separated by a perpendicular distance PO. So the torque tau is equal to force into the perpendicular distance PO. To calculate PO, we consider the triangle OPS. Let theta be the angle between the magnetic field and normal to the rectangular loop. Then the angle PSO is also theta. So in this triangle OPS, if you find sin theta, that is equal to PO by PS, that is equal to PO by B, where B is the distance between P and S. Hence, PO is equal to B sin theta. Substituting for the expression in torque, we get torque tau is equal to force BIL into PO, which is B sin theta. So torque tau is equal to PIL B sin theta. Here L into B gives the area of the rectangular loop. L is the length and B the breadth. Therefore, torque tau is equal to BIA sin theta. I into A is the magnetic dipole moment of a rectangular loop that is represented by M. So torque tau is equal to MB sin theta. In vector form, vector tau equal to vector M cross vector B. So this expression gives the torque acting on a rectangular loop in a uniform magnetic field. The magnetic dipole moment of a circular current loop. We consider a circular current loop carrying a current I and having an area A. This current loop will act as a magnetic dipole. The magnetic dipole moment M is given by M equal to IA. Magnetic dipole moment of a revolving electron. Consider an electron revolving in a circular orbit around the nucleus. Let R be the radius of the orbit. When an electron moves along a circular orbit, it consumes a current. The current I is given by E by T, where E is the charge of electron and T is the time period, which is the time taken by electron to move along the circular path once. But T is equal to 2 pi r by V, 2 pi r being the circumference of the orbit. Substituting for T in the first equation, we get I equal to EV by 2 pi r. The magnetic dipole moment is given by mu L is equal to IA. Here mu L is the symbol used to represent the magnetic dipole moment of electron. So mu L equal to I into area, where area is pi r square. Substituting for I, we get EV by 2 pi r into pi r square, or mu L equal to EVR by 2. We multiply the numerator and denominator by ME, where ME is the mass of electron. Then we get the equation mu L equal to E by 2m into ME into VR. Here ME into VR is the angular momentum of electron and it is represented by L. Therefore, mu L equal to E by 2 ME into L. From Bohr's second postulate, we have L is equal to NH by 2 pi. This is called the quantization condition. So, you substitute for L and we get mu L equal to NHE by 4 pi into ME. So this expression gives the magnetic dipole moment of a revolving electron. Here H is called Planck's constant. Now for an electron in the first orbit, we know that n is equal to 1. So substituting, we get mu L is equal to EH by 4 pi ME. This value is called Bohr magneton, and Bohr magneton is the smallest value of magnetic dipole moment for an electron in an orbit. The value of Bohr magneton is 9.27 into 10 raised to minus 24 ampere meter square.
Moving coil galvanometer. A moving coil galvanometer is a device used to detect electric current in a circuit. It consists of a rectangular coil PQRS suspended between the poles of a magnet. The other end of the coil is connected to a spring and to the terminal. The suspension fiber has a mirror attached to it to measure the deflection produced. The principle: a current carrying rectangular loop placed in an external magnetic field experiences a torque. The torque acting on a rectangular coil placed in a magnetic field is given by NIAB sin theta, where N is the number of turns, I is the current, A is the area, B the strength of the magnetic field, and theta the angle between the normal to the plane of the coil and the magnetic field. For a radial magnetic field, theta is 90 degree and hence sin theta becomes 1. Then tau is equal to NIAB. Due to this torque, the coil deflects. Let phi be the angular twist of the suspension wire. Then the restoring torque developed will be given by tau equal to K into phi, where K is the restoring torque per angular twist. At equilibrium, the restoring torque must be equal to the deflecting torque, that is K phi equal to NIAB, or I equal to K by NAB phi. I equal to G into phi, where G is called galvanometer constant. G equal to K divided by 10 AB. You can see that I is proportional to phi, or we can say that the deflection produced is proportional to the current flowing through the galvanometer. Current sensitivity. Current sensitivity of a galvanometer is defined as the deflection per unit current. Phi by I equal to NAB divided by K. Voltage sensitivity. Voltage sensitivity is defined as the deflection per unit voltage. Phi by V equal to phi by IR, where V equal to IR from Ohm's law. That is equal to NAB by K into 1 by R. Here phi by I is current sensitivity, so we get the expression NAB by K in this equation. So you can say that voltage sensitivity phi by V equal to NAB by K into 1 by R. Conversion of galvanometer to ammeter. Ammeter is a device used to measure electric current. A galvanometer can be converted to ammeter by connecting a low resistance S called shunt resistance in parallel to it. Here G is the resistance of the galvanometer. S is the shunt resistance. Ig is the maximum safe current that can flow through the galvanometer. I is the current which we want to measure. Since only Ig current can flow through the galvanometer, the remaining current I minus Ig will flow through the shunt resistance. Since the galvanometer and shunt resistance are connected in parallel, the potential difference across them will be equal. Therefore, I minus Ig into S equal to Ig into G, or S equal to Ig into G by I minus Ig. This gives the expression for the shunt resistance. Conversion of galvanometer to voltmeter. A galvanometer is converted to voltmeter by connecting a high resistance R in series to it. Here V is the potential difference to be measured. R is the high resistance connected in series with galvanometer of resistance G. Ig is the maximum safe current that can flow through the galvanometer. The applied potential difference V, or the potential difference to be measured, must be equal to sum of the potential difference across the galvanometer and the resistance R. That is, V is equal to Ig into G plus Ig into R. Ig into R equal to V minus Ig into G. Rearranging, we get R equal to V by Ig minus G. This gives the value of the high resistance to be connected in series with galvanometer to convert it into a voltmeter.